forces and vectors. So your dog is eating your physics homework, as it does, and you try to get it back. You pull with a force of 10 newtons at an angle of 30 degrees from the horizontal. Calculate the components of your pull force, right? Vertical and horizontal. So force is a vector because it has a magnitude and a direction. In this case, we are given both of those. So let's start by drawing a vector diagram to help us out. So it just says 30 degrees from the horizontal. It doesn't say if you're moving toward the right or the left, so we can choose. I'm going to choose to the right. So here's our physics book, and you are pulling with 10 newtons of force at an angle of 30 degrees from the horizontal, right? And so your dog, here's your dog's mouth. How do you draw a dog? That looks like Harambe. Anyway, your dog is pulling the other way. So let's calculate the components in the vertical and horizontal direction. So whenever you have a two-dimensional problem, you should start by specifying the positive directions. So for us, I'm going to define to the right and up as positive. And so your pull force can be split into a horizontal, so to the right, and a vertical, so upwards, force. So I'll label that as Fy for the force in the y direction, the vertical direction, and Fx, force in the horizontal or force in the x direction. So let's work out Fy first. So looking at our diagram, we have a right angle triangle formed by our vertical and horizontal vectors, with the 10 newtons being the hypotenuse. So from the angle 30 degrees, we are looking for the opposite, Fy, and we are given the hypotenuse. So we'll use the trig ratio sine. Sine of the angle equals opposite, Fy, divided by hypotenuse, 10. And solving for Fy, we get 10 sine 30 is equal to Fy. And you can actually skip to that second line whenever you're looking for the vertical component and you're given an angle measured from the horizontal. And we can compute that, 10 sine 30, 10 sine 30, making sure our calculator's in degrees, giving us 5. So Fy equals 5 newtons. And it would be upwards, right, as shown by our diagram, which is why the answer is also positive. Now in the horizontal direction, we are looking from the angle 30 degrees, we are looking for the adjacent, and we know the hypotenuse. Right, we also did work out the opposite, but I recommend you don't use that. Just in case you rounded your answer, then this answer will be a little bit off. So using the cosine ratio, so cos of the angle equals adjacent, Fx, divided by hypotenuse 10, like before, multiplying both sides by 10, and then calculating it. 10 cos of 30 degrees, 8.66. And now, what should we round this to? Well, the force, 10 newtons, is given as one significant figure, so we should round our component to one significant figure as well. Making sure you do leave that answer there, because that's useful in further calculations. There we go. We've split are 10 newtons of force at this angle 30 degrees into a force to the right, 9 newtons, and then a force up, 5 newtons. Now part 2, if the homework is stationary, how much force is your dog pulling back with? So, if it is stationary, what does that imply? So stationary implies the speed is 0. Right? It's not moving, it's stationary. Which means if there's no change in speed, acceleration is 0. And by Newton's law of motion, we know that the net force must therefore be 0. Right? The forces are balanced. The tug of war between you and your dog, right? Your dog is pulling back with as much force as you are pulling. In order for there to be a net force of 0, so there's no acceleration, so it's stationary. Yeah. So we could say that the dog is pulling back with 10 newtons of force in that direction. Yeah. However, part of that will actually be the weight of the dog, right? Because the dog has mass. So if you're trying to pull it up, you're not only pulling against the dog's like pullback, you're actually lifting them up. But to simplify it, we can just say that it's 10 newtons in the opposite direction. So dog pulls back with 10 newtons of force. Instead of being 30 degrees, we would say, what is that, 30 plus 180? So that's 210 degrees. Let's just draw that on a diagram. Alright, so 30 degrees plus the opposite direction, we'd add 180 degrees. So at an angle of 210 degrees clockwise from the horizontal. Right, as shown in that diagram. And that would result in net force being 0, meaning it's either traveling at a constant speed or that speed could be 0. Alright, and after a while of tug and war, you end up in the kitchen where the floor is smooth. Explain why your dog starts slipping. So, in order for the dog to slip, what needs to be happening? So if the floor is smooth floor, tells us that friction is reduced, right? Both for the dog and for you. However, if you are wearing, let's say, some grippy indoor like socks or something, your friction won't be as affected, whereas your dog with its cute little paws will have much less friction. And so what does this mean? This means that the dog how do we word this? So that the dog's pull force is greater than the friction between it and the ground. This results in you having a greater force, or a greater pull force, making the dog accelerate, as the net force is no longer 0. Yep. So first point was acknowledging that a smooth floor means that there is less friction available. Part 2 is linking that to the dog's pull force. So when you pull on something, you need to be firmly planted on the ground, and the ground is then resisting how much you pull. And in the case of the dog, unfortunately, there wasn't enough friction for how strong it was. And then that resulted in you having the upper hand, right? You had a greater pull force, making the dog accelerate and move along the ground, since the net force was no longer 0. And this can be reasoned with a vector diagram, for example. Alright, now that was exhausting, so now you need to sit down. Conveniently, you design a wall-mounted fold-out chair, like so, right? You have a wall, you have a bit of wood, and it's connected to the wall with a string. The seat has a mass of 1 kg. Calculate the weight force of the seat, and then looking at tension force, angles, and adjusting the position of the string. So weight force is mass times gravity, and we know the mass of the seat is 1 kg, and we know that gravity is 9.8 meters per second squared, giving a weight force of 9.8 newtons. Right, that's with no one sitting on it. Part 2, state the vertical component of the tension force in the string for the seat to be stationary. Alright, so the string here is providing a tension force towards the wall, and part of it will be acting upwards, and part of it will be acting to the left. Yeah. And for this seat to be stationary, this upwards force must be equal and opposite the downwards force of the seat. And where does that come from? Well, that comes from the weight of the seat. So in fact, this upwards force must be at least, well, exactly, right, 9.8 newtons to balance the weight force of the seat. So part 2, for seat to be stationary, and I'll put in brackets vertically because we haven't talked about the horizontal components yet. The net force must be 0, so the vertical component of the tension, so Ty, must equal the weight force of the seat, which is 9.8 newtons. Right, so we have the weight of the seat, and then we have the vertical component of the tension, and these are balanced. Now it is a little bit different because the center of mass isn't in line with where the string's attached necessarily, and then we need to do a torque analysis, but on the bigger picture, this is what is required of that tension force, right? Ignoring the torques, because it would sort of work itself out where it's attached to the wall. Alright, if the string was at 30 degrees, calculate the tension force in the string. So now we're told this angle in here is 30 degrees. Work out the resultant, right, the dark blue arrow, work out that tension force. So as a diagram, we have perfectly straight arrow. That is the tension force. Assume that that line intersected. And it's at 30 degrees. We know that the vertical component, Ty, is actually 9.8 newtons. Now, of course, there is a horizontal component too, right, to the left. But we're looking for the hypotenuse, T, the capital T, the tension force. So from the angle of 30 degrees, we know the opposite, and we're looking for the hypotenuse. So we will use this sine ratio. Sine of the angle equals opposite, which is 9.8 newtons, divided by hypotenuse, which is the tension force. Now rearranging for T, we'll multiply by T, and then divide by sine 30. So the tension force equals 9.8 divided by sine of 30 degrees, which is 19.6 newtons, or as, how many sig figs do we round it to? So the mass was only 1 kg, and that was one significant figure. So our tension force rounded would be 20 newtons. Right? And 9.8 newtons is going upwards, and we could work out how much is going to the left if we wanted. And finally, how could you change the position of the string so that it can support more weight? So let's have a look at that last question we did. So looking at that equation, so tension equals the weight force divided by sine of the angle, right? And we want to adjust the angle so that we could increase the weight force. So one way to approach this is to consider the extremes. So if we have the seat, what would happen, let's just attach the string in the middle, what would happen if the string was perfectly flat? So that red line is the string. How much weight could that hold? So that's when the angle would be 0 degrees. What about if the string was perfectly vertical? And so that's when the angle would be 90 degrees. Right? Which seat would you rather sit on? I know I'd prefer, well, the string's kind of in the way, assuming it's on the edges. This would hold much more weight. In fact, this one would just give way immediately, right, and rotate about its pivot point. So when the angle approaches 90 degrees, we can support the most weight for the same tension force. So let's try put that into a few words. One thing we need to assume, so assume string has same tension force as in the question. In other words, like this string can only support so much weight as defined by its tension force. But what we can adjust is the angle. So in order to increase the weight force, that the seat can hold. We want to increase the left-hand side, but we can't change the maximum tension of the string because it's the same string. But what we can change is the angle, and we know that sine, or the graph of sine theta, looks like this, and it has a maximum when theta is 90 degrees and a minimum when it's 0 degrees or 180. So the closer we can get to 90 degrees, the larger this left-hand side would be, giving us a greater weight force that we can support. So as theta approaches 90 degrees, it can support more weight. Now there are some limitations that you might have realized. We'd need to then attach it to the ceiling, right? So it's no longer wall mounted, it'll be ceiling mounted. So then it's a swing. Yeah, so ideally, you'd want the string sort of near the edge, near this edge, but attached really high up on the wall. That way it'll approach 90 degrees. So of course there are limitations in practice. But the key points are just realizing the relationship between the weight force and the angle, right? Graphing out sine theta if you can, and stating your assumption about the tension force. Alright, that's it from me for now. Have a great day.